Hi, this lesson is about one-to-one functions and their inverses. A one-to-one function is a function that for every element in the domain, there is only one unique element in the range. So unique means that none of the y values can be repeated. For every x, there must be one y value where that y value is not, if they are not repeated. If they are repeated, then the function is not considered to be one-to-one. So you can identify if the graph of a function is one-to-one by using the horizontal line test. That is different than the vertical line test. The vertical line test is used to determine if the graph represents a function. Horizontal line test is there to check if the graph represents a one-to-one function. So the way the test works is if any horizontal line intersects the graph in more than one point, then the function is not one-to-one. So in the first example, y equals x cubed, this is considered to be a horizontal line. So imagine if I had like a ruler laid out horizontally, and if I was able to scan that ruler all throughout the entire function, no matter where I cross that graph, I would only hit the graph once. There would only be one point of intersection. That makes it a one-to-one. The example on the right, the graph of 1 over y equal to 1 over x squared, that is not a one-to-one function. There are infinitely many places where a horizontal line would cross this in 2 points. So here's one example, here's another. So if it intersects the graph at more than one point, then it is not considered to be a one-to-one function. So again, going back to the original definition, that means that when x is 1, I have a y value up here, but when x is -1, the same y value is repeated. So the y's have to be unique. So therefore, the second graph is not a one-to-one function. Okay, so if a function is one-to-one, then you can find an inverse function for it. So an inverse function is a function that basically undoes the action of the other function. So if f and g are inverse functions, then if I took the composite f of g of x, if f and g are inverses, then f of g of x would just be equal to x. And the reverse is also true. If I do g of f of x, the answer would just be x. So in other words, the input value would be the answer. So no matter what x is, when you take the composite of two inverses, you just get the x back. So if f and g are inverses, then the domain of f of x is the range of g of x. And the range of f of x is the domain of g of x. That is unique to when f and g are inverse functions. So what that means is if x and y is a point on f of x, then the reverse is true. Y and x is a point on g of x. Again, because the domain becomes the range and the range becomes the domain of the inverse function. So the 2 points reverse. So there is special notation to indicate an inverse function. So the inverse of f is written like this. That is read as the f inverse of x. It is not f to the -1. So do not treat that notation as a negative exponent. In other words, this is not true. The way we normally deal with negative exponents, x to the -1 would equal 1 to the x. In this case, x is a negative exponent. But when it's written with respect to functional notation, that just means that it is the inverse function of f. And so therefore that relationship is not true. Okay, so all linear functions of the form y equals mx plus b have inverses, because any function of this form would be 1-to-1. So you can find the inverse function pretty easily. Horizontal lines are not do not have inverse functions, and vertical lines are not functions at all. So a horizontal line of the form y equal b would fail the horizontal line test. Vertical lines, well, they fail the vertical line test, so they're not even functions, so they don't have an inverse function as well. So here's an example of a line in the form mx plus b. F of x is equal to 3x minus 1. And g of x is equal to also another linear function equal to 1/3 x plus 1/3. And the question is asking us to show that f and g are inverse functions. So I'm going to use the definition that I mentioned earlier, that if f of g of x equals x, then they are inverses, or g of f of x. So I decided to show f of g of x. So that means that the g of x, this piece, gets input in here where the x is. So that's what you see here on the right. It's 3 times, and then the x gets replaced with 1/3 x plus 1/3 minus 1. Then I have to simplify that. So I distribute the 3 across that. I have 3 times 1/3 x plus 3 times 1/3 minus 1. The 3's cancel here and here. So I'm left with x plus 1 minus 1. The positive 1 and the minus 1 cancel, so my answer is just x. So since f of g of x equals x, the functions are inverses. The same would be true if you did g of f of x. You don't have to do it twice, but the difference would be that this would be replacing the x in here. So I would have 1/3 times 3x minus 1 plus 1/3. And then I would do the same work. I would distribute the 1/3, and that would give me 1/3 times 3x is just x, and 1/3 times minus 1 is minus 1/3 plus 1/3. The minus 1/3 and the plus 1/3 cancel, so your answer is again just x. Same answer we got here. So both of those simplifications that I did on the left and on the right both result in a value of x, and so therefore either one of those would demonstrate that f and g are inverse functions. So there are steps to find the inverse of a function. So in this case, they were given to you, and we had to prove that it was true. But sometimes you need to find the inverse. And so the steps are as follows. So if your function is stated in terms of f of x, you replace the f of x with y. Step 2 would be to swap, make the y into an x and the x into a y. If you have more than one x, then all the x's change to y. Then you solve for y. And then once the y is isolated on one side, replace the y with f inverse. So once you get to step 4, you have found the inverse function of f of x. So here's an example where we're going to use exactly those steps. And I've given you another linear function, which means an inverse will exist. So I have f of x is equal to 4x minus 5. So step 1, so I'm following these steps, and this is step 1, is replace f of x with y. Step 2, change the y to x and the x to y. So that's step 2. Then step 3 is I have to solve for y. So that's these 2 steps. I need to get the y alone. So I added 5 over to the left side, and then I divided everything by 4, and I also rearranged it. So I put the y on the left. So I have y is equal to 1/4 x plus 5/4. And then step 4 is to change the y to f inverse, and so you have found the inverse function of the original is 1/4 x plus 5/4. You can always check to make sure that you didn't make a mistake by taking this, and if f of f inverse of x is just x, then you know you did it correctly. And this one is correct. Okay, so here we're going to apply the same steps, but this is not a linear function. This is actually a rational function. So let's see how we apply these steps. So depending on the type of function that you have, the work to solve for y might be a little bit different, or maybe a few more steps. So step 1 is I replaced h of x with y. This is step 1. Step 2, make the y into an x and the x's, there's 2 of them, into y's. So that's what happened from there to there. Then I'm on step 3, solve for y. And all of this work is step 3. So first thing I did here was I cross multiplied. So I have x times y plus 9 equals y. Then on this line, I know that I need to solve for y, but right now I have y's on 2 different sides of the equation. So I need to get my y's on the same side and then be able to isolate it. So I distributed the x, and that gives me the second line here. So it's xy plus 9x equals y. Then I subtracted the y on the right and moved it to the left, and I subtracted the 9x, and it went from left to right. So I'm left with xy minus y equals negative 9x. Then I factored out a y, because remember you're solving for y, so I just want one of them. So I have y times x minus 1 equals negative 9x. Then divide both sides by x minus 1, and you get y is equal to negative 9x over x minus 1. And then step 4 is to replace the y with h inverse of x, and your inverse function is negative 9x over x minus 1. And again, you could check to make sure you didn't make a mistake by doing h of h inverse of x. And if that equals x, then you did it correctly. You could also check, is h inverse of h of x equal to x? Either one of them would be your check. Okay, here's one with a radical in it, and we're asked to find f inverse for f of x equal to the square root of x plus 1. So I'm pointing out here that there are restrictions on the domain, and this will be important later. The domain, because we don't want any negatives inside of a square root, is from negative infinity from negative 1 to infinity, including negative 1. And your range will be all positive numbers, including 0. So I'm going to follow the same steps. Replace the f of x with y. This is step 1. Swap out the y for x and the x for y, so that's step 2. Then solve for y, and so these 2 steps here is step 3. So I get y is equal to x squared minus 1. So remember, x squared minus 1 is a parabola, and a parabola looks like this. It would have a vertex at 0, negative 1, and it would look like this, which doesn't really make sense because this is definitely not 1-to-1, because a horizontal line would touch this parabola in 2 places. So that's the graph of what we believe the inverse function is, x squared minus 1. So that means that there must be some restriction on the domain of this function. And remember, I mentioned earlier that the domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. So this is the domain of the original, domain and range of the original, and when you swap them out, this is the domain and range of the new function. So because of this restriction here, the graph actually does not look like the parabola. It's going to look like half of the parabola. So this is the graph of f of x, the one in blue, but this is the graph of f inverse, the one in this hot pink kind of purpley color. It's half of the parabola. So the domain becomes really important here. We're only graphing the inverse function on the right side in quadrants 4 and 1. And then here's another unique thing about the graphs of inverse functions. When you graph them, the graph of one is the mirror image of the other, and the mirror is the line y equals x. So if you can imagine flipping the blue graph over this line y equals x, you would get the half parabola, the inverse x squared minus 1. And the opposite is also true. If you were to flip this half parabola x squared minus 1 over the line y equals x, you would get the original function, the square root of x plus 1. Okay, so here's one for you to try. Find the inverse function of g of x equal to 5 over x plus 1, then determine the domain of g of x and g inverse of x. Right, so that's for you to try. Good luck.